Consider a 10 meters MP supported steel I-section beam. In this animation, we will follow the complete load path from the uniformly distributed load through reactions and internal actions to the stresses developed inside one selected cross-section. Before applying load, notice the section geometry. The two wide flanges are efficient in bending, while the slender web connects them and carries most of the vertical shear. Curve fillets soften the flange to web junction and reduce local stress concentration. The left end is a pin. It restrains horizontal and vertical movement but allows rotation. The right end is a roller. It restrains vertical movement while allowing horizontal expansion. Together, they create a statically determinate, simply supported beam. Now, uniformly distributed load of 20 kilonewtons per meter is applied over the full 10-meter span. Each downward arrow represents the same load intensity. The load increases gradually, allowing us to see how force enters the beam. The total applied load is W times L equal to 200 kilonewtons. Because the loading is symmetric, equilibrium divides it equally between the supports. The upward reactions are therefore 100 kilonewtons at the pin and 100 kilonewtons at the roller. As the load builds, the beam bends downward in sagging. The supports do not translate vertically, so the deflected curve returns to zero at both ends. The slope is largest near the supports, while the maximum vertical deflection occurs at midspan. For this example, steel is taken as 200 gigapascals and the second moment of area is about 0.002063 meter to the fourth. Euler-Bernoulli beam theory gives a maximum elastic deflection of approximately 6.3 millimeters. The displayed deformation is exaggerated so that its shape can be studied. Next, examine the shear force diagram. Starting from plus 100 kilonewtons at the left reaction, shear decreases linearly under the constant distributed load. It crosses zero at midspan and reaches minus 100 kilonewtons immediately before the right reaction. Bending moment is the area under the shear diagram. It is zero at both simple supports and varies parabolically across the span. The maximum sagging moment occurs where shear becomes zero at midspan with a value WL squared over 8 or 250 kilonewton meters. This sequence reveals the differential relationships. Load intensity controls the slope of the shear diagram. Shear controls the slope of the bending moment diagram. Constant distributed load therefore produces linear shear and a parabolic bending moment. To inspect the internal actions, we cut the beam 1.5 meters to the right of midspan and remove the right portion. Equilibrium of the retained part reveals a bending moment of 227.5 kilonewton meters and a shear magnitude of 30 kilonewtons. Sagging moment compresses the top fibers and stretches the bottom fibers. Longitudinal normal stress follows sigma equals my over oi. Its magnitude varies linearly with distance from the neutral axis, reaching the largest compression at the top surface and the largest tension at the bottom surface. At the centroid neutral axis, longitudinal bending stress is zero. The material there neither lengthens nor shortens due to pure bending. Moving away from this axis increases the normal stress in direct proportion to y. Vertical shear is carried mainly by the web. Its distribution follows tau equals Vq over It. Shear stress is small near the outer surfaces, grows toward the neutral axis, and reaches its maximum within the web. The flanges contribute primarily through horizontal shear flow. The final view combines the complete response, applied load, support reactions, deflection, shear, bending moment, and cross-sectional stress. In design, these results are checked against strength, serviceability, shear capacity, lateral stability, local buckling, connection forces, and code requirements. Every arrow represents part of one continuous load path.